Now moving on to the second part of our conference, which is Topcon cell production equipment and materials. The first presentation is from Leadmicro. Boachen LIAO is going to talk about PECVD-based deposition solution for polysilicon layer in Topcon mass production. He is the chief scientist at Leadmicro. So, Boachen, please start your presentation. The floor is yours.
Thank you, Chauvin. Let me see, able to see, are you able to see my screen already?
Yes.
Okay. So good afternoon to everyone. Yeah, I'm Boachen from Leadmicro, and thanks Taiwan News for giving me this opportunity to share our latest progress. And it's really my pleasure, to be here to share with our latest development in PECVD-based deposition solutions for polysilicon layers in Topcon mass productions, which has been attract a lot of attention this year. So in this presentation, we will share with you our journeys to development these new technologies. So we will talk about the Leadmicro's PECVD polysilicon solutions, as well as our gigawatt scale mass production progress. So a little bit short introduction about Leadmicro. Actually, Leadmicro, we are a global equipment manufacturer specialized in development, design, manufacturing, and the service of the advanced thin film depositions for industrial applications. We probably are well known for the ALD depositions, and recently we also developed our PECVD type of thin film deposition tools. So for the ALD and the PECVD milestones, actually our company was established in 2015, and at the beginning we are introduced the batch type of ALD in the solar cell applications to replace the inline type of PECVD. So since from 2019, we start to develop our PECVD tool with the integration of the PALD technologies from Leadmicro. And the last year, for this new technology, we reached a lot of breakthroughs. Actually, based on this PECVD and the PALD process, our Topcon average cell efficiency reached 24.65 by end of last year. So in this year, we are mainly focused on mass production of this new technology, which is we are going to share with you details very shortly. So this is our company's product series. So we started with a QAF series, which is a thermal batch type of ALD. In today's presentation, I'm mainly to talk about our Zhurong series, which is basically is a tube type of PECVD platform and integrated with our own developed PALD technologies. So first, let's have a quick look about the trends of the Topcon solar cell development. Basically from the ITRPV, as well you can see from the left graph, for both carbonic oxide and the polysilicons, there is a trend to moving to in-situ deposition or in-situ doping. So this is in line with our development in PECVD technologies. If we look at the right-hand side the chart, actually you can see the blue color LPCVD technology was slowly replaced by the newly developed PECVD technology, which is in yellow. And you can see this development actually is quite in line with our development very well. Actually, you can see we have the breakthrough in the 2021, and in this year we already see the mass production announcement expansion for these new technologies. So actually a little bit background for this new technology. Actually for this tube type of PALD technology, actually in recent years has been studied quite intensively, both in China and as well as internationally. In this area, we also have a long history of technology accumulations. So basically we start the study of the Pacific contact in 2013. And in 2015, then we received a Pacific contact project from Singapore government, and mainly focus on the PALD Pacific contacts. And in 2017, another 2 years later, we received an industry project, which is for industrialization of the Topcon solar cells and with 150 megawatt. So after successfully complete these 2 projects, yeah, we integrate all the experience together. Hence, come to this new technology, which is we combine the PEALD plus the PECVD poly plus Topcon together to resolve the bottleneck for the problem we have encountered earlier. So to be specific, actually we introduced about 5 new technology, which is highlighted in red color, to solve main 3 key problems faced by Topcon. One is the front side aluminum oxide. We introduced ALD and the PEALD technology versus the traditional PECVD technology in PERC. For the tunnel oxide, we introduced the PECVD and the PEALD technology versus the traditional thermal oxide. For the polysilicon, we introduced PECVD and the LPCVD. By the way, all these technology are all based on tube type of the equipment in favor to the mass production requirement of the cost and the maintenance. Yeah. So for this talk, we are mainly focused on the tunnel oxide and the polysilicon. Yeah. So a little bit advantage of the ALD, as we can see highlighted here, is ALD. The advantage is atomic layer control, thickness control, high density, pinhole free, and also has 100% conformality. So this adding a lot of values when we develop the high efficiency cells. If we come back to this page, actually you can see the tunnel oxide thickness is very, very thin, less than 2 nanometer. How to control this 2 nanometer thickness in sub-nanometer scale proactively? Probably ALD is one of the ideal method, which we will show the data later. Yeah, based on all this new technology, we also developed the process based on this P process for the Topcon manufacturing. So today we are mainly will share with this highlighter process, which is based on PECVD, tunnel oxide, and PECVD poly. Before we go in details, let's have an overview for all the mesh production technology which is already available in the market. The first one is based on the ion implantation. It's bought by the Jolly Woo. Yeah, the second solution is based on LPCVD intrinsic poly with the phosphorus diffusion. This is currently under mass production by JinkoSolar. But the solution 3 actually is using the PECVD in situ doped poly. This method is brought by Jolly Woo as well. Yeah, today we are going to mainly share is the solution 4 and 5, which we use the PECVD as main method to develop the tunnel oxide and in situ doped polysilicon. So for the solution 5, both tunnel oxide and polysilicon are used PECVD method. This method is also known as 3-in-1 tech. But for Leadmicro, we also introduce one more option, which is based on the PEALD tunnel oxide. So hence our technology is compatible with the PEALD. So our one is so-called 4-in-1 technologies. So for the PECVD silicon oxide plus the PECVD poly, for this method, actually we have 1 gigawatt scale mass production actually in Tongwei Solar. For the PEALD silicon oxide plus the PECVD poly, we have 1 gigawatt scale mass production in Suntec Wuxi. So for the reason why we choose the silicon oxide using the PEALD and PECVD, actually the reason is very simple, as just now explained. The tunnel oxide thickness is very thin. How to control this thickness in sub-nanometer scale proactively? And the large area uniformly repeatability required for the mass production, probably ALD is one of the ideal choice. As well, you can see the right-hand image here. Even with the G12 size wafers, we can do the deposition very, very uniformly. Yeah. As our PEALD technology is built on the PECVD platform, so obviously it's so compatible with the PECVD silicon oxide process. Second one for polysilicon actually is a comparison between the LPCVD versus the PECVD method. The LPCVD method actually is well known for the drawback is the wraparound and also the operating cost, the crosswalk tube depositions. So the PECVD method, in contrast, it can resolve all the bottleneck faced by LPCVD method. Firstly, you can see the wraparound. You can see the white color at the edge is less than 1 millimeter. The second advantage is due to the plasma, which is enable the in situ doping, but without affecting the deposition rate. you still can do the in-situ doping at a high deposition rate. And due to this in-situ doping, it's also resolved the yield issue. It's very easy to clean. We will share later. The second thing for the operation cost, actually, you can see the bottom graph, right side, the bottom graph here. We all know the tube type of PECVD system actually is based on the direct plasma principle. So only the yellow color you see here, only the graphite bulk area, we have a very high intensity of the plasma, which you have a high deposition rate. However, at the quartz wall area, the plasma density is very low, and as a result, the deposition rate also very low. And our system has been in the field for more than 3 years and close to 1 year's mass production already. We never encountered problem to replace the quartz wall tube due to the deposition. So this is perfectly resolved the bottleneck faced by the LPCVD method. So this page is a summary between this LPCVD and PECVD method in terms of polysilicon deposition rate, polysilicon clean, and the mass production. As what we can see here for the LPCVD method single site deposition with the phosphorus diffusion, we will have a yield issue, polysilicon cleaning due to the BSG and the PSG etching rate different. Yeah, if we do the in-situ doping, we'll know then the deposition rate will drop dramatically. So for the double site coating, then your equipment will be double, as well as your maintenance cost will be double. So as you can see here, only the PELD and the PECVD method is a perfect method, can meet all the requirements. Yeah, that's the reason we moving towards to the PECVD method, as we shared with the projection earlier. Here are some characterizations to further illustrate the advantage. As you see from the ECV, we can achieve a very good uniformity and repeatability even on the G12 size wafers. For the TM image at the bottom, you can see that even with the ultra thin silicon oxide around 2 nanometers, we can do a very uniform deposition even along the texture surface. This shows that it's inherited the ALD's excellent conformality. This also means you will get a higher quality of passivation and the tunneling. With all this advantage, here is sharing the tool we brought to the market, which is we are probably the first one integrated the PELD and PECVD technology together. With this integration, then is enabled, you can do the in-situ tunnel oxide, you can do the in-situ polysilicon doping, you can do the in-situ element doping, you can do in-situ various thin film depositions. You can switch between PELD and PECVD methods as what you need. And furthermore, the doping level is tunable with the in-situ doping and the high yield, low cost. With all this advantage, it enables our Topcon solar cell VOC greater than 715 millivolt in average. So this page, we were going to share with you our latest development and the progress. Actually, we are the first one, probably the first one to introduce the tube type PELD and PECVD process and prove the feasibility of technology. And we are the first to achieve the cell efficiency above 24 in last year, May. Yeah. Actually, we in 2020 September, we first breakthrough is the PELD aluminum oxide technologies. Yeah, so this work has been published in PIP this year and also enabling the lab performance basically for the industry. Yeah, PELD is well used in the high efficiency solar cells. So we basically transfer this technology into the mass productions. Yeah, so this one also fill in the gaps for the ALOX deposition and give us one more options for the ALOX deposition in industry. And this work also has been selected as a featured cover for PIP in this issue, which will be released very, very shortly, probably in another 1 to 2 months. Yeah, after fix the front side aluminum oxide, then we can focus on the Topcon cell, the real side of the thin films. Yeah, the first thing we are trying to tackle is the PELD silicon oxide. Yeah, we successfully breakthrough this technology in February last year. So basically, this technology also fill in the gaps and also provide us one more options to do the tunnel oxide depositions. As you can see, many review articles haven't included the PELD method as one more option for tunnel oxide. Here we fill in the gaps. So after this, in last year June, we successfully breached the PECVD Institute of Polysilicon. This is also a very, very big challenge. We have encountered a lot of issues along the way. Here, due to limited time, I make it short just to share two major problems we have faced with this technology. One is the equipment issue, one is the process issue. For the equipment issue, actually, everyone probably quite familiar with the tube type of PELD or PECVD system. Basically, in the prep time, we use this PECVD system to deposit mainly as the insulating films, like the silicon oxide, silicon nitride, silicon oxide nitride. Yeah, this is the first time, we are using this tube PECVD system to deposit conducting film. So why the conducting film is very challenged? We use this graphite board as an example. As well, you can see the graphite board here, the left graph. Actually, the graphite board, you can see the neighboring two plates actually has to be separated by the one of the yellow color insulating ceramic rings. Why has to separate? Because the two plates has to conduct the AC current to generate the plasma. However, when you depositing the conducting film, you can see the right hand, the image, the silver color. If the insulating ring become conductive, your neighboring two plates will be joined together. So your IC current will not work anymore. So this is one of the key problems. You have to redesign your PELD system to enable it to do the conducting film. Otherwise, it will never work. So this is the bottleneck for the equipment part. So for the process part, actually, we also quite well know, and many people also criticize for this PECVD method is the blistering problems. But this one also, thanks to the community, our solar community, we works very hard. For the past 1 year, we studied very intensively, and through the understanding of the underlying mechanisms, now we all know there are more than 4 or 5 methods you can suppress the blistering problems. So with all this breakthrough in the equipment as well as in the process, finally this technology is ready for mass production. So after 1 month, in July, we received the Tongwei 1 gigawatt mass production order. So from that onwards, we are trying to resolve the mass production issues. The first thing we resolve is we integrate the PELD and the PECVD technology together. This one will enable us to do the in-situ tunnel oxide. So your tunnel oxide no need to break the vacuum. You can finish the tunnel oxide, continue with the PECVD poly depositions. So with this integration, it not only give us a high quality tunnel oxide, it's also give us 15% more of the throughput. This is very critical for the industries. So from the September to end of the year in 2021 is mainly for the equipment moving for both two projects, for Tongwei and the Suntec, both two projects. Both two projects started to mass production from January. We are finally transferring from the pilot line to the mass production. At the beginning, to be honest, at the beginning, the yield is less than 50%. We start to doubt ourselves again, whether this technology is really just in the pilot line, whether it can be transferred to the mass production, because the yield is very, very low. After another half a year's hard work, and we resolve all the yield problem one by one, until today, our yield can reach greater than 97. This data can check from the field, and sometimes the yield is higher than 90, even can reach higher than 98. So this yield rate actually is also one of the advantage, is much higher than the LPCVD methods. And furthermore, there are 2 milestone worth to mention. That is in August this year, our PECVD Silicon Oxide and PECVD Polysilicon, the gigawatt scale mass production cell efficiency surpassed 25% based on our customer data provider. In just 1 month later, in September, our PELD technology, silicon oxide plus the PECVD poly, also surpassed 25%. So with all this data available at the 1 gigawatt scale production, also give our cell manufacturer confidence to further expand this technology with an even bigger scale of mass production. That's, you see all the announcement at the second half of this year. Many tier 1 company has moved into this direction with all this data support. Yeah, this work also has been published in this year.
I'm sorry to interrupt you. You have to really finish in 1 minute. Okay.
It's very, we are almost there. At last, we share our some smart the Topcon the solutions. The 2 projects we are just sharing now, one is in Shanghai, one is in Tongwei. This is how our equipment in the clean room for the project. And this is our big data and analysis and the AI system for smart manufacturing. Yeah, here we come to the conclusion. Yeah, today we have shared with you the latest progress and our journey in the PECVD tungsten oxide and the PECVD poly development, as well as ALD silicon oxide and PECVD poly. And we also share our 2 cases with the gigawatt scale mass production based on the PECVD poly silicon. Yeah, that's all for my presentation today. Thanks for your attention. Yeah.
Okay, thank you very much for the presentation. So quickly, one question. So for both the approaches, you mentioned about 25%, but which one is better?
Based on we do have our data. I have one. Yeah, from here you can see this is a comparison between PALD and PECVD, and we also do a bigger scale comparison. Actually, the efficiency for PALD will be slightly higher, 0.04% at this 25 scale.
Okay, so anyway, thank you very much for this nice presentation and overview. Please stay back and answer if there are any questions in the chat.
Yeah, sure. Thanks, Chairman.